is Maurice Fallon, and I lead a research group that develops navigation and mapping algorithms for mobile robots, specifically dynamic robots that are moving reasonably quickly or aggressively in complex environments. So a lot of field robotics. A little bit about my background as a research scientist in MIT in Boston, working in environments as diverse as marine localization and navigation, body-mounted systems, and then I had a change of direction to move into navigation and sensing systems for legged robots. An opportunity came along to be involved in a large challenge, a DARPA Robotics challenge. It said that you should, if you're working in an American university, you should work in one and one only DARPA Robotics or DARPA challenge. They come along every few years, and it gave me the opportunity to work closely with organizations such as Boston Dynamics, who loaned us this humanoid robot known as Atlas that many of you will be familiar with. And over the course of several years, we developed the algorithms for the robot to walk, to carry out manipulation tasks that were teleoperated from remote operators, and to navigate semi-autonomously in its environment. And different research strands, we made that more or less autonomous. Moving to start my own independent research group, I focused on a slightly simpler problem of four-legged robots, taking from the adage of Animal Park, 4 legs are better than 2. And there I focus on navigation and perception algorithms. And I'm going to talk a little bit about the capabilities and technologies we've developed over the years. So legged robots, as the sensing systems have improved, embody many of the same sensor payloads that you find on autonomous vehicles. For example, lidar sensors indicated with the blue arrow, commonly used for autonomous vehicles to sense and to range in their environment, visual cameras, but also sensors that are specific to the legged system. So for example, in each of the robot's joints are encoders that measure force that are used to infer the forces that the robot is impacting on the ground and how it's moving. But there's also sufficient onboard compute to do quite interesting algorithms. To motivate the trust of my research today, I got involved in a second challenge run again by DARPA, and this involved using these quadrupeds that we were working with in collaboration with organizations such as ETH in Zurich, who did a lot of the controls work that we're doing here. Mostly I was focusing on navigation and mapping. And the challenge framed by DARPA in this particular case was to explore underground mines, to build very accurate maps of those mines, but also drove forward the integration and the robustness of legged systems such as this animal quadruped that you can see here. So exploring in confined and entirely dark environments, you can see that it's carrying on board its own lighting so as to be able to project enough light into the environment to be able to do what was effectively a treasure hunt, identifying fire hydrants, mannequins corresponding to maybe personnel that needed to be recovered. And you can see an illustration of the graphics from DARPA illustrating the sectors of the map environment that were being built. So mapping was a central aspect of this. Ron Arkin's going to speak later, and he was involved in the team from Georgia Tech and CSIRO that were also involved in this challenge. And this is to give you an idea of some of the perceptual challenges. On the right-hand side, you can see some pictures of the robots that we used at different phases of the competition. You can see in the bottom right how dark it was. You might just about be able to make out that there's standing water, so puddles in the environment. So some of the sensors that we use when pointing directly at puddles or standing water, just see that as a blank chasm where the robot could fall in, which obviously can't be distinguished from actual chasms where the robot could fall in. And you can see the unevenness of the terrain in the top right. So focusing on the left-hand side, you can see some of the perceptual challenges of building a very accurate map of this environment. In this particular experiment on the top left, the robot enters a mine and then walks down 2 different sections. Very elongated sections like this are very difficult for navigation algorithms to work reliably. And you can see in the lower left the footprint of the laser scanner. Each of the individual, there's 16 beams on this particular lidar, which shows you that it can only really sense the walls but not the ground. So it has a difficult time constraining its motion estimate using lidar sensing. The circles correspond to visual features that have been tracked, which are very difficult to maintain and track over an extended period of time. So our contribution in this challenge was to develop multisensor odometry to fuse together the different sensor sources, and I'll talk a little bit about how those algorithms work. So the first components that we worked on were leg odometry. So these are the internal sensing of the robot's joints and foot contact sensors. And this is an illustration of the challenges that you have when working with these kind of sensors. On the left-hand side, you have the idealized case, where the leg of a robot, the quadruped in this case, but also the Wondercraft robot that you saw yesterday, as it steps and places its foot on the ground, in the idealized case, it's able to detect when its foot's in contact and use the self-motion of the robot relative to that foot to infer its body velocity. But in the realistic situation, you're walking on soft ground, which causes the foot to sink in. The foot might slip if it's on slippery brick, for example. And then the actual metallic, or the actual structure of the robot, particularly for heavier humanoid robots, tends to bend, meaning that it's a sensor modality that exhibits continual drift. It has no external sense of the environment. So here you can see a trace in green of the robot walking along this kind of bricky, gravelly environment. And you can see two different estimators, one developed by ourselves and one developed by the manufacturers of this robot, that continuously drift because they don't have any external sense of the environment. So this first piece of work, we incorporated external vision sensing, so visual inertial odometry, which fuses together the sensor measurements from the camera system, so tracking corners and edges in the images, and did this in a manner that allows it to holistically combine together the different modalities into a single estimate. So I have a few different references to this kind of graph representation, so I'll take a second to explain it. In X, on the horizontal axis, corresponds to timestamps of where the robot is over time. Typically in the order of 10 of these nodes are placed down every second. The characters M correspond to visual corners that have been sensed in the scene, and the green lines correspond to constraints that we're building to them so as to combine together the different modalities. And it's solved as what we call a least squares optimization problem with an open source library called Georgia Tech Smoothing and Mapping GTSAM. And here you can see an illustration of the system working. So the yellow dots here correspond to the 3D points that have been tracked in the camera and then projected into 3D space. We have a green line from an external tracking system, which gives us the ground truth of the motion. And you can see the blue line that's been estimated from tracking the robot up and down this gravel path is very accurate. But the lidar tends to be a much more accurate sensing modality. It's able to measure out to 80 meters and is actively transmitting light. So the lidar, this is the sensor just under this camera system here. So the lidar is a very accurate sensor, but it's a power-hungry sensor. So what we wanted to do in the next phase, as we moved into the challenge that I talked about, was to find holistic ways to fuse together vision, lidar, inertial sensing, and also the joint sensing from the robot. Typical approaches would run a visual tracking system, like I described previously, separately from a laser-based system, but in these confined environments where you can sense your distance, your position in that long tunnel corridor, but you don't necessarily know how you're moving along it, then the lidar is not very good at giving you longitudinal estimates, and the visual feature tracking is kind of stable. But if the robot was to walk to face a wall, so you've got this holistic. We want to achieve a holistic fusion of the different sensor modalities in a sort of unified approach, and the way we did that is to bring them out and fuse them together on a constraint level. So we have our constraints from our visual features here shown as yellow dots. And they're tracked in a relatively standard approach, a KLT-based feature tracker running at about 10 hertz or more. And then with the lidar, we take the lidar scan. It's a scan of points around the environment in which we're able to detect patches of planar features. So for example, patches of the walls of the building here, or edges which would correspond to vertical structures such as corners. we can establish constraints between those and track them over time. And in doing so, we now have more manageable individual features that we can track over extended periods of time. I won't go into technical details about how this can also help with this optimization problem that's indicated by these graphs, but some of the innovations we contributed in this space were how to keep this graph representation on the right-hand side simpler than the one on the left-hand side, and then which take into account the fact that, for example, the laser sensor continuously scans its environment rather than instantaneously capturing an image or a lidar scan at a particular time. So there are these technical challenges that are maybe beyond the scope of this particular presentation. So this is an illustration of all of those constraints now being added into a single factor graph representation that's effectively a moving history of the environment around the robot. It's kind of a goldfish memory, so it only retains a history back to maybe 10 seconds or the spatial location where those visual features are present, and it's solved as a sort of a windowed estimate. So give you a few impressions of. So this is the same environment that I was talking about previously. The robot is pursuing a route down this mine tunnel, and you can see visual features in yellow, and the green patches correspond to the ground plane and the sides of the surfaces present in the environment, and it's building and maintaining this accurate representation. That's both to allow it to autonomously explore, but the other aspect that we contribute to is building this terrain map, this colorized rainbow pattern around the robot's feet, which is then used for the robot to do footstep planning, and that's kind of the main input to the reinforcement learning algorithm to make a decision about how it should move. And that was the work of our collaborators in ETH. So you can see that this is an accurate representation of the environment at all times. But a local representation, and as we moved into a mature system, we wanted to break the link back to the legged system to make it less tightly integrated on the walking robot. And you can see here we sort of tightly integrated the sensor system, so the laser and the camera system, into this modular payload that could be carried by a person or mounted on different robots and still be able to retain these components. And then to scale that up to maybe large-scale environments, so large-scale mapping, we retain this concept of a factor graph that you can see again here, but this is a much more sparse factor graph representation. The factors now are laid out only once every maybe 1 meter or so. They correspond to local snapshots of the laser data, and here we illustrate building up a large-scale laser-based map. And as this particular data set explores into an environment on the right-hand side and closes this loop, just in a second you can see that the map is being continuously adjusted to take into account local odometry drift and to correct the factor graph. So this is a second tier of estimation that runs at a slower pace, separate from the high-speed sensor fusion for the odometry that I talked about previously. But it allows us to build more accurate large-scale maps. And as we moved into maybe 2022, we started putting a lot of effort into accurately measuring the quality of the maps that we were producing. We had a collaboration with a company called Hilti from Liechtenstein, who work with construction technology, and certain use cases in the construction sector are unlocked by the increasing accuracy of this technology. As the accuracy of the maps that are being produced starts to be, say, within 1 to 2 centimeters of ground truth, then they can be used for things like progress monitoring. So we ran a challenge with Hilti, laboriously scanning both a construction site and a historical building in Oxford called the Sheldonian Theatre, with this high accuracy tripod on the left-hand side, which literally took 3 days of closing the theatre to be able to get a very accurate scan. And then the handheld device that Linton in the yellow jacket is carrying is then used to collect data for accurate mapping. So you can see here an example of the construction site data fused into a single map. So this is not just a single map of that individual run, but it's a series of maps carried out over the same day. Each of the green line corresponds to the path that Linton took as he carried the device around through the environment. And each of the poses along the green line are accurate to within 1 centimetre. We combine those together by finding constraints, or doing what's called place recognition, so visual and lidar place recognition in particular, to find constraints to link the maps to one another. You can see red lines at certain points, depending on the visualization, that indicate constraints that have been added to bring mission 1 and mission 2, as illustrated on the right-hand side, into alignment with one another to form a fused map. And that becomes the basis of being able to infer change. So over dynamic environments like security applications or the construction sector, you're able to bring these maps into continuous alignment, align them in addition to maybe a building model as shown here, and to infer the changes that have occurred. In many cases in construction sector, those changes have been incidental. They might have been decisions that were made by a site engineer when building a portion of a building, but not actually communicated back to the person who's maintaining the building model. So this red, or the red patch in the top right was a extension to a room on the first floor that was not reported back into the building model. So these are the kind of things that result in errors in the construction sector. We formed a growing company now to try to develop this technology commercially to build what we call a 4-dimensional model of the environment. So 3 dimensions, but also with the extra dimension of time. And just to reiterate, this is handheld as opposed to robotics. It indicates maybe the challenges of working in very dynamic environments, as we saw yesterday, where there are both plant equipment and also people moving. And robots need to be able to move around an environment like this without obstructing them. And I would say at this stage, this is a stretch beyond where robots can be reliably deployed. So shifting back to legged robots, the animal environment, the animal, as we saw exploring the underground mine, was actually a pretty pivotal step forward for legged systems, because they actually outperformed the wheeled robots that were originally originally expected to be the best performing teams in that underground exploration challenge. But nonetheless, this was the kind of environment where the robot was operating. It is quite a challenging unstructured environment with loose stones, but it's kind of shrink wrapped in a sense, in that there is no natural growth, there are no wires or cables or trip hazards. A piece of work that we've done since in collaboration with ETH again was to allow the robot, which mechanically is well able to walk through this kind of foliage that you can see on the left-hand side, but with its depth sensing cameras is completely confounded by what it sees around it. The right-hand side is the representation from the cameras in the robot's belly and the robot's head that are pointing at the ground, and they're sensing this foliage and assuming it to be an obstacle. So instead of trying to classify these as obstacles, we need to instead look at where the robot has the capacity to traverse. Typical approaches in autonomous vehicles are to do a lot of hand labeling, to label different classes of objects. Here you can see an illustration of a fixed set image segmentation for autonomous vehicle, segmenting things into bicycles, road surfaces, foliage, and so on. In a natural environment, there's a very continuous transition from the kind of grass that the robot can trivially walk through to bushes that are more difficult, but the robot can achieve it, through to thickets or dense trees where the robot cannot. Or maybe specifically classifying those into individual classes is a very difficult task, in particular when lighting conditions change. So instead of taking this approach that requires a lot of hand labeling, work that we've done instead looked to use a supervisory signal from on board the robot. So when the robot is brought to a new environment and we want to fine-tune or to train its capacity to distinguish where it can and can't walk, well, we can first give it a minimal amount of supervision in that environment using the hindsight of where the robot has walked. So the robot in this still is walking up and to the left, and the blue carpet that's behind it corresponds to the terrain on which it's walked. So if we have the images pointing at the terrain corresponding to where it walked just a few seconds ago, we can use those to distinguish the terrain that the robot's able to classify. So in effect, the lower part of the image, of the three images that you see here, can be associated with a control signal that indicates that this particular terrain is traversable. So that's a self-supervised approach to a natural environment terrain traversability classification, as illustrated here. So the important factors for the system to be able to quickly tune or to train a classifier in the wild that can run on board the device, and to do so in a matter of a small amount of demonstration time. So here you can see an example of the time taken for it to be able to effectively distinguish where it can walk. It's not really classifying where it cannot walk. It's really preferring to walk where it's been successful before. So the approach works by segmenting the image into different pixel clusters and then using visual transformers to carry out self-supervised classification. And here you can see as you go from top left, zigzagging downwards in the images, there are three loops that of the same environment. Gradually, it's able to distinguish from a uniform heat map across the image in the top left to gradually being able to distinguish the terrain where it can traverse. And this can then be, this is another example of it being able to distinguish between the natural foliage, which geometrically is a challenge for the robot to walk through. So there's high thickets, I guess. It's not quite grass, but it's a thicker material underneath it, sort of ivy maybe. The robot's able to distinguish that it can walk across that, but because it's not given any demonstrations of walking through trees, it's able to distinguish to avoid that. So we wanted to apply this in a practical sense. One collaboration project that I actually have with Cyril, who'll speak after me, is to develop technologies for digitizing forests, to develop a more sustainable forestry technology by having drones and legged robots to be able to build accurate maps. And one of our collaborators are developing a semi-autonomous system for light harvesting. So we're bringing the animal robot out into these kind of environments, using the laser technology that I described before to build up map representations of the environment. This is just showing a live map being built on a handheld system here, being carried through the environment. We switched to a backpack because you need to be able to really get in amongst the foliage, to pull it apart, to find your way through, to clamber up hill surfaces. But with the backpack mapping system, we're able to get out and really map large-scale environments. So this is a portion of a forest in Finland, and you can actually see the footprints of the person walking through snow in Finland there as the map is being built around. So porting that onto the legged systems, here's some initial demonstration of the autonomy is not particularly complicated. It's a lawnmower pattern-based exploration using this multi-sensor classification about where the robot can and can't walk. This initial part is just on an access road. But when it turns into the environment, it's effectively following a carrot on a stake to iteratively go between each of the inspection points while motoring around obstacles that it finds along the way and replanning as needed. On top of that, we started to build components and systems to build what are called martelloscopes, which are kind of a standard forest inventory representation for summarizing the contents of a forest. So going from the raw LiDAR data on the left-hand side, terrain segmentation, individual instance segmentation, extracting individual trees, fitting their diameters, cropping away the canopy from each of the individual trees to have a measure of the height, and also we're moving towards developing measures of the quality of the growth of the tree, if there's a deviation or a bending of the individual tree, for example. The system is successful in this kind of environment. Maybe it might look benign. We take it to somewhere maybe adjacent or quite challenging, and this was a test environment in Finland where the robot was operating in what turned out to be quite deep bog, and it's sunk down to about 40 centimeters into the ground. So you can see the knee of the robot is visible, but the actual shanks are entirely sunk down into the environment. It actually sucked off the robot's foot, and we lost that into the mud of Finland. So if you're hiking in Finland, maybe keep an eye out for a robot's foot. So switching slightly to something a little bit more close to home, I've wanted to continue the interest I had in legged systems and humanoid systems, and I maintained a connection through an EU project to the team at Wondercraft. I think we saw this video playing yesterday. I'll play it for a few of the people. This is a very motivating demonstration of the exoskeleton technology that Wondercraft are developing, and I've stayed in touch for a few years and seen how the system's ability to walk on has become smoother, more integrated, and the technology that they're developing is much more fluid, and as you can see, walking independently outside on the Parisian streets. So I wanted to do some work to explore what could be done to add some more situational awareness, hypothetical to this system. We sort of have a loose collaboration with Wondercraft. We hope to do some more over the summer. And I've been working with Marianne and Fabio and Francois as well, kind of semi-independently of the Wondercraft team. We've developed a leg-mounted multi-sensor mapping system, as illustrated here, that potentially could be installed onto the robot to, independently of the robot, visually build up a map representation of its environment, so that the exoskeleton can ambiently build a visual map of its environment and to be able to identify the obstacles of its environment. So it's a bit clunky at this stage. You can obviously see that it's about twice the size that I would like it to be, but you can envisage that we would like to have it installed in around the lower legs of the robot, which means that inherently it's going to be impacted upon by the leg motion and the swinging motion. And I'll just talk for a few minutes about the technologies that we've been developing to build up a kind of situational awareness for a leg-mounted visual mapping system that take advantage of language models. So visual language models such as the CLIP classifier is able to take general images as illustrated there and to return general semantic understanding. So to be able to carry out semantic understanding of what's in the scene, answer queries that are maybe more open-ended than fixed set classifiers that I talked about previously. And we wanted to use those to do classification of of the individual rooms. Now, we haven't done as much as we haven't fully solved this problem or gone very far, but we've done semantic classification of multi-floor buildings. So building upon the multi-sensor odometry system that I talked about previously, and here are some results with that sensor box on the left-hand side that I talked about previously. The camera system has wide field of view camera images and cameras facing in different directions, so that, for example, with a walking system, in certain situations, certain cameras become useless because they're pointing at blank walls or they're subject to aggressive motion blur. But having this large field of view allows us to have more robustness to these kind of challenges. So I'll just show. This indicates the large field of view of the cameras. If you look here, you can see three different camera images. One for a forward-facing camera, one in the very middle, one for the left-facing camera on the left and on the right. And these visual features are indicated as circles, but where there are lines that span between camera images, that they correspond to portions of the images that are jointly seen and visual features that are tracked. And I'll just show one result to kind of illuminate its value. So here you can see very aggressive motion by the visual tracking system, and it's still able to maintain an accurate track. Here's a college in Oxford, a very narrow doorway of a medieval college building, and as the system is carried up a staircase, it's able to interchangeably switch between tracking of the camera features from different cameras. You can see as it goes up the staircase initially, the forward-facing direction is good. The left, the visual features are flowing past and they're not stable. But then as it turns, there are few visual features in the forward direction. So you can switch between the cameras implicitly by selecting which camera features to track over time. And then building on top of that, the language model-based semantic classification, we lay out a kind of another pose graph representation, but the nodes now are then labeled according to which room classification they have. So in different colors correspond to corridors, offices. The individual offices kept separately and clustered together with a labeled propagation algorithm to maintain a coherent clustering of the individual rooms. So this shows the system being carried by the handheld still. Each of the colored nodes corresponds to a snippet along the trajectory, which corresponds to, which is colored according to the scene classification. Again, using visual language models, which have presented themselves as being of equivalent performance to the engineered approaches that have been typically used, so bag of words based approaches that have been used for visual place recognition. So it's a combination of a more traditional place recognition system with large language model based image comparison. And this is just to show that the map representation can continuously adjust by recognizing when it's come back to a certain location. You can see the map sort of being moved around gently as recognition of returning to a location has been achieved. So moving on to something that's specifically to do with the exoskeleton, was mapping the terrain of the environment and moving those sensors onto this leg-mounted system that you see here. You can see that the motion of the sensor payload is quite dramatic. It moves in a manner that's a bit like what you would get on a ship. So continuously moving upwards and downwards. And by using these wide field of view cameras, the system can track features for an extended period of time without losing visual feature track. This video shows a sort of larger scale environment, and it's the lower left is the visual footage that we're trying to track off of. And it's a bit difficult to watch at certain points because of the degree of undulation that you have in the natural walking motion. But despite that, we're able to track motion over an extended period of time. Closed loops and to build up this visual map. And I'll just quickly show that we also build a terrain map of the environment, and we can build large-scale maps of environments that can then form the basis of navigation around the environment. So this is a multi-floor map of an environment segmented into where the robot can walk, where it cannot walk, and we want to work towards developing an integration with the Wondercraft robot to demonstrate some sort of mid-level autonomy for the exoskeleton. Okay, that's all I wanted to speak about, and thank you very much for your time and attention this morning.
Thank you very much, Maurice, for this inspiring talk. You addressed many different aspects of perception for autonomous systems, so that's quite interesting. And I think it raised interest and maybe questions from the audience. So we have time for some questions. Is there someone else for the microphone? No. Yes.
Thank you, Maurice. Very, very interesting. So, haven't been following the developments, the detailed developments of this field, but a few years ago, I remember it was a kind of a dream to have a robot or a person visit an environment, take data, and then send another one on that map to execute whatever task. Mm-hmm. It seems that we are there, basically, from what I understand on this talk, and this is great. So my question is, how do you see this in the future? So these maps will be available, will be maintained. Does it make any sense that you have maps that only need updates? Is there any sense in making robots that build maps and then sell maps to other robots for use in an environment? And in the long term, how do you see these develop in the future?
Well, my talk kind of intentionally focused on the geometric reconstruction of the maps, not necessarily very, very detailed focus on the semantics of the maps. So I think the semantics is what Cyril will talk about, and I think that's where the value the value for robots interacting with map representation. So moving away from point clouds and images to actual object level inference and object level understanding. So I think that we are at a point where photorealistic maps can be built by representations like NERF representations, which I didn't talk about today, which starts to become unimprovable. You're achieving photorealism with some of the map representations that are now become available. But understanding what's actually in them is the next challenge, and how they can be afforded with, how you can actually interact with them. In terms of a marketplace, I mean, there's a pretty well-developed marketplace for autonomous vehicle maps or just on-road mapping. For them to be interchanged or sold, I think you described, that really depends on the circumstance, but I haven't really thought very much about that.
Thank you.
Yeah, first a question here.
Thank you. I really enjoyed the talk. Now, the use of the receding history to classify the terrain, I really like that. Is it one of those things where the operator is eventually lets go of the control?
Yes.
And then it's developing a confidence in its terrain that it can do that?
Yeah,
can you talk more to that?
Yeah, I mean, a standard approach, particularly autonomous vehicles on road environments, is to have large data sets that are labeled and then developing your learning algorithms that can be used immediately. But this approach is intended to operate in very lighting, uncontrolled environments where something that you labeled even in that environment in the morning can no longer be used. So it's intended to be something that can be quickly bootstrapped and deployed. So it's in the order of a minute of teleoperation before being able to autonomously operate with point-to-point navigation thereafter. That was the goal. Yep.
So in terms of operationalizing this, is it something where after a minute the operator is running it and then it's got enough confidence to say, I've got it from here, and the operator can go back to what they were doing?
That would be the approach. I wouldn't say we've tested it to the extent that where you have boundary leakage as you move towards a path that gradually changes because maybe you're moving from a limestone to a sandstone terrain, and there's very subtle changes. But this is how it can gently meld as the traversability classes actually vary themselves is something that we want to explore more. But this is the performance capability that we would seek. It might be that we would rely on lidar sensing to give the robot to allow it to autonomously be able to do the first supervision. So put it in an environment where the lighting conditions match where you want it to operate, where it can learn how it should operate, so it doesn't need the human being to give it that first 1 or 2 minutes, and then have it rely on vision thereafter. But this is the approach of initially bootstrapping it, recognizing that visual navigation in unstructured environments is very difficult.
And is there, so I like the calibration run idea, but what about can it detect when it's no longer accurate? I'm getting into an unknown area, that my classifications are going to go false positive.
Well, it intends to stay traveling on environment which it has seen and understood previously. So to go into environments where it can traverse but it hasn't been given a signal is a limitation of the approach. So we would not seek for it to explore into the unknown to put itself within danger, for example.
Does it know it, is the question.
I would say
that requiring a human to supervise and say, oops, nope, we're getting too far out.
It wouldn't go into that kind of environment because it wouldn't have an example of when it was there previously. But I would also say that... But what
if it doesn't have a choice? I got lost.
It would find no possible route and it would stop.
Then it would stop.
Yeah.
Yeah, thank you very much, Maurice. I can see indeed that the field has grown tremendously. It's very impressive. I have two questions. So the first one is so typically when your robot was traveling in Finland, I think, it lost its leg. And when I do travel in forest, I do use vision, but I use primarily haptics. So I was wondering to which extent you're doing multimodal sensing. Same for the exoskeleton that you have. when you want to regain the balance and the frame of reference, I would expect that one would also couple this with, you know, some proprioception or some with. That's the first question. The second one is, since you combine it with LLM, I see that the map is incredibly dense. But similarly, when I navigate, I do remember only a few things, and this will completely depend on what I'm looking for. So to which extent are we there to be able to change the granularity? And maybe following up on Robin's question is to also decide when I'm inferring makes sense and when it doesn't.
The first one is a little bit easier to answer. The locomotion capability that Mark Hooter's team in Zurich have developed means that the robot struggles to fall over. It can plod along without tripping because it's quadrupeds have a low center of mass. They're kind of like a walking table. When it walks into a bush, it will just bump against the bush continuously, but there's no sense that it's physically pushing against something other than the fact that it's not making progress. So I have a collaborator in Oxford who works on soft robotics, Perla Miolino. We're interested in adding contact sensors to the front torso of the robot to allow it to be able to perceive that it's making contact, and then in doing so redirect itself on the basis of a direct sensing rather than just a lack of progress of the walking controller, if that makes sense. Well, at the moment we haven't fitted it with these kind of sensors, but if you're struggling to make progress in a certain direction, then you can add that as an obstacle in your map representation. But if you rewind a few years of the progress of these legged robots, when they were using model-based controllers, simply making contact with the outside world would result in them falling over. So we're in some sense, we need to raise our expectations to be able to have contact-rich autonomy, and especially for this kind of natural exploration that I've tried to explain. Okay. Second question, I might have to ask you to state again. The map representation? You mean the...
How do you, I mean, is there any easy way to modify the granularity and to really pay attention to certain features, depending on what you're looking for? And typically the trees here, you may care about those that are usually that are sick versus those that aren't, or those that are tall, or a certain type of trees, or just not caring about trees anymore because you're looking for animals, you know. So I'm just asking, when you combine this with LLM, to which extent are we close to be able to modify the granularity? And the granularity seems incredibly high, which will create problems, of course, for sharing maps and sharing knowledge.
I think like the mapping work that we've done here is very classical classification-based work. It's only in the indoor environment that we've been doing this LLM-based approaches. We'd like the map representations we're building of these forest environments to only retain the specific details about the individual tree instance coordinates, their dimensions, and to leave behind all of the semantic details about, or all of the dense point cloud data that we're leaving, because it's not really realistic to maintain gigabyte maps of forest environments.